week. That's his. All right, very good.
All right. Morning, everybody. Hi.
Get started. A few announcements. So we want to set up a time for K office hours. So I'll send around a poll, and please fill it out so we can see what we can do to accommodate the most people as possible. So the first problem set is now on the web, as are the lecture notes. We'll get the videos posted. They'll be there on YouTube for time immemorial. So the first problem session will discuss this assignment tomorrow. Okay. All right. So I want to continue with our review a little bit to get ourselves reoriented to lots of things that we have been talking about, that we talked about last semester. And, what we're talking about is classical versus non-classical light. Of course, fundamentally, we have a quantum mechanical description of the world, but there are certain states of the quantum system which, for all intents and purposes, we call classical. And let's remind ourselves about that again. So we have coherent states, which we also call quasi-classical states of the quantum field, which I'm writing like this, which is a tensor product of coherent states in every mode, whatever mode decomposition, okay? And these have the property that they are eigenstates of the annihilation operator with eigenvalue given by the classical complex amplitude in some units associated with that mode, okay? And coherent states have the property that the expectation values of the quantum field, say the electric or magnetic field, are equal to the classical field. So that's the number one important property of coherent states. The expected value of the electric field operator is what we would expect for a classical field with those mode amplitudes, okay? And moreover, that it has minimum quantum fluctuations consistent with the uncertainty principle. So the reason this is quasi-classical and not just classical is that we still have the uncertainty principle. We still have, even though we might be able to find the expected value of certain things, it doesn't mean that every measurement will yield the same outcome. There will be shot-to-shot differences in the measurement outcomes depending upon what we measure, and those fluctuations we're calling quantum fluctuations, okay? But the coherent states has the least possible.
Why is it on the right-hand side, is it substituted by alpha or k, not just alpha?
No, that's just, yeah. Right, okay, but these states are pure states. Even though they're pure states, it still means that you can still have fluctuations because of the uncertainty principle. But in addition, we can have classical statistical fluctuations, classical noise that is different from what we might call this, sometimes called quantum noise. Okay, but we could have classical statistical fluctuations. So what we have said is that we're going to define classical states as the general class of mixed states that include the classical statistical fluctuations, which means they are a statistical mixture weighted by some probability distribution where this is a positive semi-definite function, okay? So this is a statistical mixture of occurrences, and this are the classical fluctuations. This way of expressing the density matrix is something we'll talk about again more in a few weeks. It's the Glauber-Sudarshan P representation. And in principle, any state can be written this way, but if it's a state that's not a classical state, this won't be true anymore. In fact, what we'll see is for almost any quantum state, this thing will be highly singular and not even very well defined. Okay, but we could in principle write a formal solution to that. And so what we, again, said last time, I'll just quickly remind ourselves again, this has certain implications for certain kinds of inequalities or bounds. So one thing we know is that if we have a classical state, then in any mode, and I'll just leave off the mode index, the fluctuation in photon number, which is the square root of the mean of n squared minus the mean of n squared, is greater than or equal to the mean n, okay? Where the minimum case is for a coherent state, which corresponds to Poisson fluctuations. And that's those random counts, those fluctuations in the number of photons one will see in a given time interval. The Poisson statistics, in some sense, can be put in without ever quantizing the field, okay? But it is consistent with the quantum description, right? So just again, to remind us, we talked about examples of classical states, that cyclical mixture. I just want to remind you about the example of a black body or a thermal state, okay? A thermal state of the field for a given one mode is given by the canonical ensemble, the Boltzmann distribution, where H here is the Hamiltonian of the field, which for a given mode is just the Hamiltonian of a harmonic oscillator with that frequency. And what we reminded ourselves of last semester is that the thermal state is diagonal in the energy eigenstates, which are the number states, with a probability distribution that is the Bose-Einstein distribution. Right? So we have the Bose-Einstein distribution tells me for at a given temperature, what's the probability of finding n photons in that mode. And the Bose-Einstein distribution can be expressed as the mean number of thermal photons to the power n over the thermal photon plus 1 to n plus 1. Remember that? Maybe. And the mean number of thermal photons is equal to the Planck formula. But moreover, we also showed that the thermal state can be expressed in the basis of coherent states. And when we did that, we found that it had a positive Glauber P representation. That's to say, the probability distribution. Do you remember what that probability distribution is for a thermal state? Or at least what kind of function is it? It's a Gaussian. It's a Gaussian. And that Gaussian is this. Okay. So this has the same form that we reminded ourselves of from last lecture from last semester, of a collision broadened, is also going to be thought of as a thermal state, okay? Where the mean n here is equal to the statistical fluctuations in the amplitude, right? So the point here is that when you have a coherent state, you have a delta function. It has a definite alpha. When you have a mixed state of this sort, you have a statistical distribution of alpha, and this is related to the intensity fluctuations that we talked about last lecture, right? These are fluctuations in the class of the fact that the intensity is not well defined from a thermal state means that there are fluctuations, and that's what this is representing. Very good. All right. And then maybe I'll say here that, you know, generally, the classical states, the ones that are the statistical mixtures of coherent states, faithfully reproduce all correlation functions or statistical correlations seen classically. So if I have a classical statistical theory, I can ask about the fluctuations and correlations in the field amplitudes and intensities, and that got us into the whole Glauber theory of statistical correlations and how he defined the coherent state in the first place. So, in particular, what we're often interested in is a situation where we can think about multiple square law detectors that each measure the intensity of the field, or for a single mode, we can say they measure the photon number, because the intensity is just the photon number. And I have some intensity at some time I measure, and I'm looking at the correlations between these intensities in some way. Now, quantumly, we have the intensity operator, which for a temporal mode is A dagger A. It's the number of photons in a particular temporal mode, as we discussed last semester. And I have some correlations, some correlator here. And the Glauber theory says if I'm looking at the n-fold coincidence rate at these different times, the way that I find that quantum mechanically, doing the full theory of photon counting, where we have a theory of photoelectric effect that now includes the quantum field, that when we did that, what we found, the answer to this, was that this was the normally ordered product of the intensities. I'll write it. So I, intensity at T1, intensity at T2, dot, 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 intensity at Tn. Or for single mode, or for temporal modes, each of these slices, I can think about this as the number in that slice, the number in that slice, the number in the last slice, etc. Where the double dots represent the normal order. Yeah?
Should that be T3
Yes, it should.
in the argument of the G function as well? Or?
It should. I don't know where that's coming from. But yes, yeah, absolutely. Who knows? All right. Very good. So let's remind ourselves, what do the symbols mean? The double dot. We're going to see it a lot more soon. The normal. This is what's known as normal ordering. Normal ordering means is a shorthand by saying the order is, A and A dagger don't commute. So I have to, when I'm writing this down, I have to decide the order of A and A dagger. And what comes out of fundamental theory of photon counting is the photon counting rate or coincidence rate depend on the normally ordered, with all the A daggers on the left and all the A's on the right. So the normally order means forget about the fact that A and A dagger don't commute. Just put all the A daggers on the left and all the A daggers and all the A's on the right. So this is A dagger T1, A dagger T2. Now I'll say it's A dagger T3, dot, 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 and then A T1, A T2, dot, dot, dot. So that's what we have, okay? Now, importantly, just again to make this connection to the fundamental theory of quantum mechanics and how it's consistent with the semi-classical theory, if I have a coherent state, and I look at Gn, then each one of these guys is an eigenvector. This is an eigenvector of all these guys. And I can replace each one of these by its eigenvalue. And this is just the complex conjugate of that. And so what I get is the mean of alpha at T1 squared times the mean of alpha at T2 squared, the mean of alpha at T3 squared, dot, dot, dot. The correlation function factorizes. This is just equal to the product of G1 at T1, G1 at T2, etc. Well, I don't, that's actually not the right, I should want to write it right. Just saying it's factorizing. I want to get into some. But let me emphasize what that factorization, what's the implication of that factorization? What that means is that the joint probability factorizes. That is to say, they are uncorrelated. So if I have two different time intervals, the rate or probability that I'm going to count some number of photons in that time interval is completely uncorrelated from my probability or rate to calculate it in another time interval. And that's the fundamental assumption of Poisson statistics. Okay, so let's see, I guess it's up here. Where did I write that down, the heavy business? Anyway, oh, here. Right, so this is why, this factorizes why the coherent state gives Poisson statistics, okay? Very good, but there are other features that we see in the Glauber correlation functions that are important to remind ourselves about. So, in particular, if I thought about a two-time correlation function, which is seen in the famous Hanbury, Brown, and Twiss experiment, where they looked at the correlation between the intensity at two different times. So we have what we call G2 of the time difference here. This is the expected value of the normally ordered n at tau. So I'm looking at the rate or probability of seeing two photons that are separated in time by some time interval. Yeah?
This is the experiment that mandated the quantization of the field?
Not really. I mean, in a sense, the original Hanbury Brown Twiss experiment was not done at the single photon level, right? If you may remember, Hanbury Brown and Twiss, well, it's really Hanbury Brown is one person, and Twiss is a stupid, they're not two people. They were radio astronomers, and they were looking at correlations between radio waves in two different antennae to try to measure the temporal correlations or spatial correlations between stars, okay? And the reason the Hanbury Brown Twiss experiment became such a hot topic and a sort of a hot button topic was that what they were seeing in their experiment, as you may remember, if we looked at this as a function of time, what they saw here was something that looked like the following. So this is the G2 function that they saw, where this envelope, this decaying envelope, was the same decaying envelope that we discussed last lecture that one sees in looking at a single detector which correlates the field with itself, which looked for classical interference of the wave with itself, and that classical interference of the wave with itself decayed when you were past the coherence length. But here we're measuring that interference not in terms of the wave amplitudes, but in terms of the intensity. And because these events have to do with two photons, people were very confused because the edict was that every photon only interferes with them itself. But this is not a single photon interfering with itself. There's no problem with that, because that is true if you're only looking at single photon counting experiment, then the interference is always describable. in terms of that single photon interfering with itself. But if I have a event that involves two photons, then what interferes are the probability amplitudes of the two photon histories. This is what we call two photon interference. Okay, so this can be understood as a two photon interference experiment. I think, you know, the Hamburg-Brown twist experiment later was done with single photon sources by Aspect, which then really did, as you go, Danny, to show us. That wasn't done by, wasn't the original Hamburg-Brown twist
It
experiment.
was an extension.
But it is an extension, yeah. Right, so, very good. So one of the things I wanted to remind you about this was that if we have classical light, then because of the form of the classical light as a statistical mixture, as you may remember, what we then found was that this object by the Cauchy-Schwarz, or who's the third guy? I forgot. Or his name already. D. Poor guy. Yeah. But such is life, you know. It's going to forever be Cauchy-Schwarz to us. But yes, that so so the Cauchy-Schwarz inequality says that if I have, you know, the dot product between two vectors is less than or equal to the magnitude of the product of the two, right? That's the Cauchy-Schwarz inequality. This thing, as we may or may not remember, can be looked at as a kind of inner product with itself of the two things, and in when we have this classical light, which tells me that this is less than or equal to the square root of that. That's the Cauchy-Schwarz inequality that follows from this being a classical probability distribution. And if we have stationary statistics, each one of these, this is actually the same as this, because it only depends on the time difference, not the actual times. So this equals that, which is equal to, so this is G2 at tau is less than or equal to G2 at 0.
How does that follow from it being a classical probability distribution?
I don't want to go through all the details of being Leroy, but if we plug this back in here and we take those expectation values, then I can take the square root of this probability and look at it as the overlap of two functions. But it's important that this thing be a positive number for that to be then the right. That's where it came from.
It's just like the complex combination.
Exactly. Yeah. So, what does this tell us? It tells us that if we have classical light, we have photon bunching. That is to say that the rate or probability of finding two photons together is always bigger than having them occur at two different times separated, okay, for any tau. So that's what this is telling us. So what we're seeing in the Hamburg-Brown twist experiment is we can interpret it in two different ways. from the point of view, we can think of it totally the way that Hamburg, Brown, and Twist thought about it. They thought about it because they were not doing quantum mechanics in terms of just random statistical fluctuations of waves. And the Gaussian nature, if we go back and think about it, the fact that for the thermal state, the Gaussian nature of those things enabled them to derive this, just in terms of the Gaussian fluctuations of the waves. But from a quantum mechanical point, we can think about that in terms of the photons, the corpuscular nature of the light gives fluctuations, and when we have a thermal state, because of Bose statistics, the bosons tend to be bunched, okay? And so it's all self-consistent. If, on the other hand, non-classical light can be anti-bunched. Meaning that the two photons never come together, they only come separately. An example of an anti-bunch source is a state that is a single photon emitter that emits single photons in a regular fashion. So if I had a beam such that in every temporal mode I have exactly one photon, then that is anti-bunched, okay? There's no such state. This is a number state. In each interval, it's a number state. It's got a single photon state in each temporal mode. It would, instead of having the alphas there, I'd say one photon in mode 1, one photon in mode 2, et cetera, et cetera. That state is a very non-classical state. And in fact, if I were to, and this is aligned with what you're suggesting, then the extension of this, if I look at this, it would look like that. There would be no possibility of seeing two photons at the same time. If my time window was sufficiently big, then I could see, oh, this one and this one, right? So it would be a signature. And often, a lot of people who are working like in quantum dots, looking at single photon emitters, what they're measuring is G2. They want to see this G2. Often we normalize this relative to G1 squared, and that's called little G2. Often you'll see that in the literature, and it's 2 for a thermal state, and it would be 1 for a coherent state, and it would be 0 if I had an exactly single photon state. Okay. Excellent. All right. So these are some of the sort of the two features that we've just discussed in terms of things that are classical versus non-classical. One is that classical states can have sub-Poissonian statistics. I mean, quantum states this would be such an example, right? There would be no fluctuations. They're sub-Poissonian in this case. And photon anti-bunching. But that's not the whole story in terms of litmus tests, things that distinguish classical light from non-classical light. So we want to talk about, remind ourselves a little bit of some of the other features. Well, those other features might be seen in different kind of measurements that we might do on the system. We've been focusing here on square law detectors and photon countings. There's other kind of measurements that we could do, which we'll talk about very soon. Homodyne and heterodyne measurements are other kinds of measurements that we can do. And they are related to other observables and other properties of the field. So I want to remind ourselves of discrete variables versus continuous variables. What do I mean by this? Well, so when we have the simple harmonic oscillator, the Hamiltonian for the simple harmonic oscillator we wrote like this just now, but we can also write it as it originally is in terms of was originally written in terms of a kinetic energy and a quadratic well in terms of the quadrature operators. So this is the number operator, which has discrete eigenvalues, and x and p are what we call the quadratures. They are the things that generalize the position and momentum of a massive particle on a spring in a harmonic oscillator. But here we should be a little more careful. Yeah, Tristan.
Are we intentionally leaving out like the plus 1/2?
Yeah, so I'm intentionally doing that. You are absolutely correct that this is actually not true. Let me put that in, because then it's actually equal. Okay, this is actually equal to this. I left it out because, as we remember, the vacuum fluctuations don't play a role in the dynamics and the measurement outcomes that we see. Because where the ground state energy is doesn't matter, okay? It's not that vacuum fluctuations are important, but the energy of the ground state is irrelevant. And often we leave it out. Maybe in quantum gravity it will matter, but for this it doesn't. Okay, very good. So let's just quickly remind ourselves about the classical simple harmonic oscillator. Which I can think about with the same Hamiltonian, and I can think about the evolution in phase space. So in phase space, we define a complex amplitude alpha, which has a real part and an imaginary part, which are the quadratures. Now, we're stuck with this horrible factor of 2 that has to go somewhere. So the real part is not just x or p, and this causes so much consternation. I was having so many fights with my students and postdocs about factors of 2, and it all comes down to this. It's just annoying, but we have to deal with it. It has to go somewhere. But the equation of motion for the simple harmonic oscillator under this Hamiltonian is that the solution is that, okay? And written in terms of the quadratures, then x is equal to the square, so again, x here is the, is equal to the square root of 2 times the real part of alpha, or alpha plus alpha star over root 2, and p is the square root of 2 times the imaginary part of alpha, or alpha minus alpha star over I root 2, and x at t thus is equal to the real part of alpha of t times root 2, which is equal to x at 0 cos omega t plus sine omega t times p at 0, and p of t is the imaginary part of this, which is equal to that, which is harmonic motion. Okay, I take the real part of this, I plug that in, I get this. Okay. So what we have in the phase space is a trajectory that looks like that, which is a harmonic motion. So this rotates on in the complex phasor space. So again, to remind ourselves, we can simultaneously think about this plot in two ways. In mechanics, this is phase space, the position and momentum, and this is the trajectory of the particle in phase space. Alternatively, we can think about this as phasor space, where this is a complex phasor, which is a complex number, and they're one and the same, like factors of root 2 times, right? And this has an amplitude and a phase as well, right? So the magnitude squared of this is related, is the energy of the harmonic oscillator, okay? So quantumly, the position operator is the Hermitian part of A up to factors of root 2, and P is the anti-Hermitian part of the factors of root 2. Okay. Again, I want to emphasize that the x and t quadratures are not the position and momentum operators of the photon. That's not what they are. They are properties really of the collective. They are sort of wave-like properties. They are related to the continuous variables. They have eigenvectors and eigenvalues, which are real numbers on the real line. Those are the eigenvectors and eigenvalues of the quadrature operators, but they don't represent the position momentum operator. What they represent are the quadratures of oscillation of the electric field. Okay. All right, so what about the equation of motion? So I can think about this in the Heisenberg picture. In the Heisenberg picture quantumly, the Heisenberg equation of motion for the annihilation operator is the same equation of motion that we just saw for the classical amplitude, the phase space of this equation of motion that we just wrote down, whose solution is exactly the same. And the time evolution of the quadrature operators thus is exactly the same as we had in the classical solution. So that's interesting for the harmonic oscillator. The expected value of x and p undergo the same trajectory no matter what the state is. No matter what the state is, the mean value of x and p follow exactly the same equations as classically. It'll go around in a circle on phase space no matter what the initial state is. Yeah?
So then this formalism is not unique to non-classical light. We can describe any optical state with these quadratures.
We can always, yes, we can describe any state with these quadratures. The properties of classical versus non-classical light will have to do with the quantum fluctuations. Okay, so what I just said is that x of t here is the classical trajectory. It's exactly this, same for p of t. But the fluctuations can be different for classical and non-classical light. Let's get there. So let's first talk about the thing that we call quasi-classical, the coherent state. So if I have a coherent state and I ask, I have the following thing. What is the mean value of the annihilation operator as a function of time? Well, we have that, right? That is a e to the minus I omega t. Just as we had classic. Well, that's true. I just said it didn't really matter whether it was a quasi-classical state or not. Everything will follow the classical trajectory. It didn't really matter if this was true, except here it really is alpha. And moreover, we can think about this in the Schrodinger picture. Okay, so what that means, of course, is that the mean of x of t is equal to x of 0 cos omega t plus p of 0 sine omega t. That's a harmonic oscillator. So I repeat, x of 0 is equal to the square root of 2 times the real part of alpha. And p of 0 is the imaginary part. Okay. What about in the Schrodinger picture? Suppose at time t equals 0, I have a coherent state. What is the state at a later time? Well, that's equal to this. Right? Which is, over h bar, if I want to put that in, which is e to the minus I integer a times a coherent state. All right, so I'm gonna, what is the answer to this? And then I'll try to remind ourselves, because there's one step things I wanted to remind ourselves of that I forgot. I claim that this is equal to this. That is to say, the state at a later time is a coherent state, but just with a different complex amplitude. So quantumly, we have a coherent state which has a mean value of alpha, a mean value of its distribution alpha. It also has fluctuations, but as a function of time, this thing rotates in the complex plane, e to the minus phi over omega t related, and every time it is a coherent state, but its phase has rotated. Okay? How do we prove that? Well, I want to remind ourselves of some phase space algebra. So let's look at the following operators. I'm going to define a phase space rotation operator. I'll call it R as a function of theta, e to the minus I times theta times the number operator. Okay? This is a rotation operator that rotates in phase space. So let's look at this object. Unitary transformation. This is a unitary operator. I claim it's a rotation operator in phase space. Why? How does it unitarily transform the annihilation operator, which is like the complex amplitude? Anyone know the answer to this, or how you would figure it out? What's that? You could use the BCH theorem to the answer to this is this. It does that rotation by that phase. Let's remind ourselves what the BCH theorem, the Baker-Campbell-Hausdorff. I don't know who I've been left out of this. I'm sure there's somebody who deserves. But anyway, is how it goes. So let me look at the following. The BCH theorem says the following. If I look at a similarity transform, of which a unitary transform is 1, and I look at that similarity transformation, that is equal to A plus the commutator of B with A plus a half the commutator of B with the commutator of B with A plus dot 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 1 over n factorial the nth commutator. So I do this n times. So this is 1 time, 2 times, and I commutated 3rd time, etc. Okay? So here I write B is equal to I theta times the number operator for A dagger A. Because when I take the conjugate, that becomes that. And A is the annihilation operator. Okay? So the commutator of B with capital B capital A is I theta times the commutator of the number operator with A. Right? Which is what? Well, you take this outside, the commutator of A dagger with A is -1. So this is equal to minus theta times A. And each time you do this, what you get is this is the sum over n, 1 over n factorial minus I theta to the n times A. which is the exponential. But of course, that's what we expect. We just said that's also the solution to the Heisenberg equation of motion, right? Because this I can think about as the time evolution operator in the Heisenberg picture is that unitary transformation, okay? Very good. So that's one of our phase-space rotation. The other thing I want to remind ourselves of, oh, before I do that, I think there's one other thing I wanted to say. So when I do this thus on, say, the quadratures, in the same way that I had that for cosine omega t, this becomes x cos theta plus p sine theta. And this rotation rotates p. This is a rotation in phase space. If I think about x and p as the coordinates of the phase space, I've rotated them, right? This is a rotation matrix on x and p that is instantiated as a unitary transformation on the operators. Now, this is something that confused the hell out of me when I was writing my notes, and then I realized what was going on. It took me forever. If I look at these, let's just write, I have a coordinate system x and p. This, I'll call this x of theta, and this piece of theta is this axis. These are what's called the phase quadratures. Okay. And I've rotated this by the angle theta. This rotation is counterclockwise. Whereas I just said the vector goes around counterclockwise. I mean clockwise. Huh? Well, the reason is that this is an active rotation on the vector. This is a passive rotation on the coordinate system. When you do a rotation operation, or any operation, you have to ask, are you rotating the vector, or are you rotating the coordinate system? If I wanted to know if I rotate the vector by a certain amount, I can ask what is projection on that. Its projection will change. Equivalently, I keep the vector fixed and I rotate the coordinate system. It's the same projection. That's why the quadratures rotate this way, but the vector rotates the other way. Does that make sense to people about how you think about whether you have an active versus a passive rotation? Okay, finally, I want to talk about one other phase space operation. Displacement. So we remember that momentum is the generator of translations in position. I'll call this the translation operator that translates me by, and the translation operator by the same BCS argument takes the operator and translates it or displaces it by the amount x. It takes the eigenvector of position operator and translates it by some amount. Okay. Similarly, I have position is the generator of translations in momentum, but with the opposite sign. I'll call this piece of P, let's call this M for momentum. Okay. So then we talked about, so this displaces me in position, this displaces me momentum, a phase space displacement operator that displaces me by some amount x and some amount p. Yeah,
Should that be a complex conjugate for M in different?
a dagger, yes, thank you.
And
Yeah, absolutely. The phase space displacement operator was something that we wrote down was symmetric. Didn't favor, because x and p don't commute, displacing in x and then displacing in p is not the same thing as displacing in p and then displacing in x. So we put the exponent together, this is symmetric displacement. And when we rewrite this in terms of the complex amplitudes and the creation annihilation operator, it has that form. Okay. I want everyone to memorize that. Okay? This is something, if you do, you need to know this is the form of the displacement operator, which we call V of alpha. Okay? Yeah.
That symmetric displacement is like saying you displace some dp dx dp dx like back and forth.
That's right. Good. So, all right, so what we remember is that the coherent state is a phase space displacement on the vacuum, right? So coming back over here, I can think about the coherent state as taking the vacuum state and displacing it. Okay. So now I want to come back. Oh, so I maybe should have some properties of the displacement. So the displacement operator what did I want to say about this? Oh yeah, displacement operator displaces the annihilation operator in the same way that translation displaces x, this guy displaces p, this guy displaces both x and p, right? Let me, before I get to this, let me remind ourselves of another fact. Two displacements by alpha and then some beta, I can compose that to the displacement by the sum of the two with a phase. We solved this for homework. This is, we can think about the set of displacements as forming a group. You take two displacements, you put them together, you get another displacement, except you have this phase. Okay. This property, again, follows from BCH. Okay? So, the coherent state is a displacement on the vacuum. So using phase space algebra, what is the probability of finding this coherent state given this one? Or the other way around, it doesn't even matter. I'll say this is alpha, this is beta. Let's say, what is the overlap between two coherent states? Well, this is equal to because this is the dagger. Moreover, the displacement dagger is just displacing backwards in phase space. So this is equal to that. Does everyone see that? And according to this group property, if I don't, this is equal to that. Okay. And what's that equal to?
E to the minus alpha x beta.
This is equal to this. That's for my, this is equal to this. How do we remember that? How do we get that? Well, there's lots of ways to think about it. So, let's look at this matrix element. This is equal to this, where this is a coherent state whose complex amplitude is alpha minus beta. So this is the probability amplitude to be in the vacuum, which is what? So we all remember, because we've memorized this really well, that a coherent state has this form. The probability to be in the vacuum is that. Okay.
Well, minus over 2 then.
Because I squared it.
Oh, yes.
So this squared is that, which is equal to e to the minus a half the difference in the x and the difference in the p. So the overlap between two coherent states falls off very rapidly. If I have two coherent states, depending on how far they're separated compared to their uncertainty. Their uncertainty is related to the vacuum fluctuations, but so this overlap is not ever exactly zero. Different coherent states are not orthogonal to one another. But they become distinguishable and very close to orthogonal when the centers of them are sufficiently separated compared to the vacuum. Is that clear? All right. Very good. So let's go back to the question I asked a moment ago about the time evolution operator. So now I said at time t equals 0, I had a coherent state. At a later time, I have the time evolution operator acting on the coherent state. which is actually, this is e to the minus I omega t times the number operator, which is the rotation operator acting on the coherent state, right? And the coherent state is the displacement on the vacuum. And the displacement operator we just memorized to be that. So this is equal to, using one of the trickeroonies that one does, is I'm going to put in an R dagger R here. This is the identity, I can do that. When this rotation operator acts on the vacuum, what does it do?
Rotates it.
And what happens to the vacuum when it rotates?
Nothing.
Nothing.
No.
So this is the identity on the vacuum. So this is equal to this on this. But then here's another trick. When I have a unitary operator, I can bring that unitary operator into the exponent. So generally speaking, if I have a unitary operator acting on a matrix exponential, do you believe that boxed equation? Yes, it's true. And the reason is if you do the Taylor series expansion, because the U dagger U's all cancel. So that's an important trick. It's a math trick, we do it all the time. Okay, now I look at this, dealy Bob. This was R at omega, this, I should say, this is R omega t a R dagger at omega t. Let's look at this object. Oh boy. That's equal to e to the minus I omega t a e to the plus I times the number operator. Right? So, what is that? So we just had this whole story somewhere about the rotation operator. And that, we said when we rotated A, it rotated it by a phase. However, we have to pay attention. Here we have R dagger R, and this guy we're having R dagger. But that's okay, because R dagger of theta is equal to R of minus theta. Okay? So, with that said, this thing is equal to a let me try to be cleaner. This is equal to a e to the plus I omega t, and this is equal to a dagger e to the minus I omega t. This is the opposite sign because this is R dagger rather than R negative R. Putting this all together, I get e to the right? So this is equal to, this is a bunch of algebra on the board, always boring to watch. The displacement operator, alpha e to the minus I omega t, acting on the vacuum, which is that. So, bottom line here is that under free evolution, a harmonic oscillator that starts in a coherent state stays in a coherent state. It has all the properties of coherent state, it's just that the mean value, and it preserves all the quantum fluctuations. So just having the free evolution of harmonic oscillator is equivalent to the quasi-classical state will stay quasi-classical. What we now want to think about, and we'll pick up starting next week for the new material, is, okay, how do we make this thing non-classical? It's not, if we just had this kind of free evolution, displacements and rotations, as we'll see, is basically linear optics. And linear optics, if you start with a classical state, you'll stay with the classical state. If it's a coherent state, it stays a coherent state. If it's a statistical mixture of coherent states, it will stay the same statistical mixture of coherent states. If we want to go beyond that, we need to go beyond linear optics. And that's what we'll start discussing next time. All right? Very good. Have a good rest of your afternoon. Yeah.
That's me.
Moving it. Yeah, I mean, you can also think about moving it. I think there's a conflict at that time. Yeah.
Okay.
Yeah.
Oh,
But
love
you
it.
can also record it. Let me look into it. Let's see what when people